then we say here that it's harder to accelerate, and that's because the mass is bigger. And so this becomes really the key statement about mass that many, many people online and in textbooks talk about. And if I could state this, a little bit different, this is what the law of inertia says. It's the tendency of an object to resist changes in velocity. And this resistance is the mass which scales the acceleration, and they call that inertia. So what I want to do here is that I want to show you some images and a video. And what you're seeing here in this image right here, you clearly see that this guy right here is a sludge hammer, right? So this guy is a hammer. And you could clearly see that this is a massive, maybe I should say massive block of rock. So then I propose this question here. What will happen to the man holding up the block? As the hammer hits it? Well, to put it in plain language, nothing. And of course, the question is, why? And the answer is, this is a massive block. But a massive block means that it has what? A huge resistance to change velocity. In other words, because the mass is so big, you end up getting a tiny acceleration, which means in this case that he feels very little. He feels very little. Oh, damn, I just closed down the video that I wanted to show you. Here, let me go get it again. Oh.
Writing's not that easy.
Okay.
Grammarly can
I gotta have this commercial get by.
Is grammatically correct.
So I'd already set this up. It's a relatively short video. So let me share my screen so you can see what I'm talking about. Here we go.
So why does the bed of nails not hurt me, by the way?
Because they're so close.
Yeah, my mask is spread out, so that pressure's not as great.
But if there was no cinder block to absorb it, and you absorb it, would you?
If you got hit by this switch.
Even if we were out of it.
Oh.
So the other thing I do is I read my physics book. And I kind of see a few prayers to Sir Isaac Newton. Now the physics book is just there so I don't catch anything in the face. I'm ready. So excited.
So let me go back to my notes and then let's check it out. So one of the things that we just saw here is that this would be an example of a bed of nails. And you know, in the old days, bed of nails did not have such a high density of nails. They were spaced out apart. And so what I did here is that I took an image of this, and I want you to look at this image, and I want you to compare it to the image above. What's the difference? Here's a big block. There's a sledgehammer. Here's a sledgehammer. And this is a concrete block. So when I look at this guy right here, what I'm seeing here is that this is the thing that's most important right here. And when I look at this, we note that this is what? This is a concrete block, which then tells us that it's what? Very massive. In other words, just like we've been stressing, that the bigger mass means that there's a tiny acceleration. So his back is lightly being pushed onto the nail bed. Now, as a counterexample, this would be very dangerous if a plastic block was used. And the reason why is that then that plastic block gets a huge acceleration. And as a consequence, his back is accelerated quickly. Into the nail bed. So there is a difference here. Okay, that's what that concrete block did here. And also the shape helped here because of the way it broke. So that being said, I want to go in and I want to talk about mass a little bit more, because most people don't use the word mass. They use the word weight, but that's not correct. So there is a big misconception. Between mass and weight. Okay, so these are the two things we need to differentiate. We have to differentiate these guys. And what I would say here is that people think these two are the same. But they're not. So let's look at this thing. Mass is how much stuff is inside an object. And when I look at the units, we then say that the units of mass is kilograms, which we typically write like this. On the other hand, weight is the force of gravity. And when I look at the units of gravity, or the units of force, excuse me, it's newtons, which we call N. So they already have, different units. So why the different units? And so when I think about the force of gravity, this is due to a planet, or star. So if there is no planet or star, then there is no force of gravity. Okay, there's no force of gravity. So what we want to do here is that I want to give you an example to get you to think about what I'm talking about. So let's look at that. I want to give you a good example. And so what I'm going to do here is that I'm going to do two cases here. Okay, I'm going to say case one. And what we're going to do that is everything that we do here is on Earth. And what I'm going to do here is that I'm going to throw a tennis ball. That you catch. So you and I are going to play catch with the tennis ball. And what do we know? This guy has a small mass. So what I do here is that when it's thrown, you easily catch it. In other words, it's easy to change its velocity. It's easy to accelerate. And the way we say this, of course, is that we say what? A smaller mass has less resistance to change its motion. But then I'm going to throw a second. Now I'm going to throw a bowling ball. And you know that when I compare the bowling ball to the tennis ball, this has a larger mass. So I throw a bowling ball that you catch. And when I do that, we know that this is harder. To catch. Why? It has a larger mass, therefore it has a higher resistance to change its motion. And so what we say here is that we say this, because it has a higher resistance to change in motion, this is what? Hurtful. This is not hurtful. But that's what we mean by that. Your body has to do that. Now, here we go. Now we want to contrast this to a second situation. So now we have case number 2. What do? We jump into the magic school bus. And I'm referring to those books that you may have read when you were young, which I think are fantastic. There's some really, really great books. So you jump into the magic school bus and up we go into empty outer space. So when I say empty, we got to be very particular here. No planet or stars, right? No planets or stars. So on Earth, when I threw the bowling ball had not only a bigger mass, but it had a bigger weight. The tennis ball had a smaller mass or a smaller weight. When we go into empty space, well, that changes. Now, what we can do here is that I can ask the following question. If I throw the same tennis ball and bowling ball at you, are any of these hurtful? And remember, because of empty space, that tells me no force of gravity. That means both balls are weightless. What does weightless mean? If I put them onto a weight scale, they would read nothing. So when I look at this, what we find here is that even though the bowling ball is weightless, it still has mass. It's the mass that causes the hurtfulness. It's not the weight. It's the mass that causes the hurtfulness when trying to catch it. And that tells you that mass is not the same as weight. Okay, mass is not the same as weight.